Now, our next speaker is Professor Howard Hayden, who is now an emeritus professor of physics at the University of Connecticut. In addition to being an extremely distinguished scientist, since I don't know much about science, I have to have this translated. He's also an extremely good writer explaining the science to people like me. And he does that through a publication called The Energy Advocate, which comes out once a month. And I would like to say I read it every month, but my colleague Sam Kasman, who has the subscription, won't share it with me every month. So I only see it part of the time. Is it on the web?
No.
It's not on the web. But if you want to have some of the basic energy issues, the most important ones in the public debate, explained in terms of what the scientific basis is, go to the Energy Advocate. It's really invaluable. And with that, please join me in welcoming Professor Howard Hayden.
Well, it's a pleasure to be speaking to this great audience, and I've heard some terrific papers already, and I'm humbled by this whole experience. It's really great. I'm going to discuss one little part of the so-called global warming problem. I'm not sure we can do that. Okay. I'm going to discuss just a little bit about computer simulations. There is a seminal paper about computer simulations. I don't know if you're aware of this thing. It's called a computer simulation of F equals M over A. Now, for those of you who have forgotten your freshman physics, the correct physics is F equals M times A. But I published that in 1984 in the Physics Teacher. It came out in the April issue, on the first of the month, as far as I recall. And believe it or not, I got some requests for diskettes. Anyway, that's the seminal paper. Global warming models are computer simulations. And primarily they are garbage in, gospel out. Now they are simulations that are based on curve fitting, not on basic physics. Basic physics has a whole bunch of equations and so forth. And, the climate itself is extraordinarily complicated, and the mathematics you have to do to solve the climate is just absolutely phenomenal. It's well beyond the capabilities of all of the craze in the world tied together. So what they do is they take a few physical principles and then attempt to, on the basis of those few physical principles, to determine the coefficients that fit in. And so they do multilinear analysis and so forth and come up with some coefficients. But the long and short of it is that they're curve fitting and not really deriving things on the basis of real physics or real chemistry. Anyway, there's two kinds of climate analysts. One of them is model makers, and the other one is gauge readers, the people who pay attention to the facts. Here is a graph that you have seen in many forms. It's the temperature record from Bostock. And it's the variation from the present. And as a physicist, I look at that and I say, there's a very distinct asymmetry that shows up in there, which I will have a lot to say about before long. But the long and short of it is, as you look at that thing, now it's reading with the past toward the left, that it covers 400,000 years. And the present toward the right, what you notice is that there so many of those curves are characterized by a rapid rise in temperature and a slow decrease in temperature. And that's a very, very important asymmetry, which I will discuss in a minute. By the way, all of those times are ice ages, and those are the interglacials. Folks, count your blessings. Right here in New York City, over in Central Park, you can find gouges in rock that were caused by glaciers rubbing rocks over the surface. Because the glaciers were, after all, a mile high. That's pretty nasty stuff there. Okay, let's see where we are. Here's the button working. Whoops. Al Gore said, with those same things, you can see how well they fit together. Let's see, is there a backup on this thing? I don't know. Yeah, anyway, one more. Anyway, Al Gore is standing in front of this huge screen showing those two graphs, and I'm good here, thanks. As long as I have to back up here. There is one relationship that is more powerful than all the others, and it is this. When there is more carbon dioxide, the temperature gets warmer. Well, an English teacher ought to flunk him right there. Temperatures do not get warm. Anyway, it's a beautiful theory, but it's about to be destroyed by a brutal gang of facts. And this is there's a question that I haven't seen really asked, but it's this: where does the CO2 come from? The CO2 rises, therefore the temperature rises. Okay. There's the CO2 history, and it goes back the same 400,000 years. There's our current rise, and there comes this question: where did that CO2 come from? Well, we certainly have an answer to that. Probably it's to be found in the comics. Wile E. Coyote, who could pull anything out of his back pocket if it was as long as it was made by Acme. There's an old adage that correlation is not causation. And I found a beautiful graph on the net, and I even then went to the trouble to find out where it came from. But it's a graph of the average global temperature vertically plotted versus the number of pirates, which decreases toward the right. And as you can see, the fewer pirates we have, the warmer it gets. Okay. There's a lot that we have to discuss about causality and that sort of stuff. The first principle of causality is that the cause must come before the effect. We've heard this business about cancer causing smoking. Al Gore may have to commit posthumous suicide. The second principle is that not everything that comes before an effect is actually a cause. And the third principle is really being ignored, I'm afraid, at this conference. There is no such thing as the cause. Now, for example, we've heard some discussions about the current temperature for the last, since the turn of the century, the temperature has remained essentially constant, and that is inconsistent with a rising CO2. Well, I think nobody ever said that CO2 is the only cause of anything that happens in the weather, and the fact that there is not a particularly good correlation over that period of time is essentially meaningless. We cannot ignore it, but it's just one of many, many facts that we have to consider. And the fourth principle, of course, is the correlation is not causation. CO2 emissions, there's a lot of CO2 that goes into the air every year, and humans are responsible for about 3 or 3.5 or 3 3/4, depending on whose numbers you use, for all the CO2 emissions that go into the air. All right, trim that thing by 1%. Now, what are you going to get? You're going to get nothing. Okay. So we're responsible for only just a few percent of the CO2 emissions into the air. The biggest source is warm water, as we've heard from several people. I was really pleased to hear Fred's talk just a while ago, and he nailed that one down very, very well. It was something that I have known for decades. After he made his comments there, when someone was speaking, I told him, that is not news. And he said, yes, you're right, it's not news. I mean, everybody's always known that. As the Earth warms up, the Earth, well, can't get that. Anyway, the two biggest sinks for CO2 are photosynthesis and cold water. And by the way, you might ask, how is it the carbon dioxide that's 4 miles up in the atmosphere gets down to Earth? And the answer is rain. You got untold trillions upon trillions upon trillions of raindrops that are very small in diameter. They are surrounded by the atmosphere that has CO2. The cold rain happens when the water cools down. The cold air goes into the CO2 goes into the cold water droplets and descends to the ground. Of course, then they can turn around and go back up, just depending. But the long and short of it is that astronomical effects are responsible for the major warming and cooling cycles. And when the warming cycles occur, then the ocean warms up. When the ocean warms up, then you get more CO2 into the air. For those of you who would like to read more about this, the magic word is Milankovitch. That's Milankovitch, who was a Serbian. The other important Serbian was Tesla. Well, not really the only other one, but the one that you will have heard of. Okay, now I'm going to show you something about the atmospheric effect. I referred to the asymmetry that one has between the rise in temperature and the descent in temperature, and I'm just choosing one of these peaks that's there in the range of 150,000 years ago. That's the only number shows up on the graph. You can just find it there. And what you find is that there is a fast rise, and the reason this thing is fast is because we have two effects working together. Let us take it as axiomatic. There is an atmospheric effect. The atmospheric effect is mostly water vapor. There is carbon dioxide. We have things like snow cover, many, many, many things, changing the albedo. So there are many things on the Earth that help control the temperature, and those things, especially the atmospheric effects, are working such as to increase the temperature over what it would be if we had a little spherical isothermal stone of 30% albedo. For those of you who don't know, albedo is an astronomical term which means reflectivity, and it refers generally to the whole Earth, and it's measured by looking at the light that reflects toward the moon. Now, in the slower descent, we have things working in the opposite direction. That is that the astronomical effects are working to cool the Earth down, but we still have the atmospheric and other such effects working to keep the Earth from cooling down, so that those are in opposite directions. So I've stretched this thing out using a stretcher, and I'm going to do a little bit of arithmetic here. I'm going to set the cooling slope equal to -1. We don't care about the units because in the end we're going to take a ratio. If you want to put that in units, that would be so many degrees per so many years. But that is not of concern right now because we're going to take a ratio. And there is a warming slope, and you can measure the warming slope. Just stretch this thing out and measure some stuff. And you see, when we have a cooling, we have the solar effect operating in one direction and the Earth effect operating in the other direction. They work in opposite directions. When we have the warming, they work, shown by the arrows there, in the same direction. But the warming slope in this particular case is 2.4 of these odd units, and the cooling slope is -1. Now we're going to put it together. And the warming rate is the solar plus the earthly. They work together to give us 2.4 times C. And the cooling rate is that the earthly effect, which is tending to warm, the solar effect is tending to cool, is equal to minus C. And by the way, the solar effect is just variations in the Earth's orbit. Okay, that's the thing. So that can warm and cool. The sun is always going to try and warm us, okay? So we put the arithmetic together. S plus E equals 2.4 C. E minus S equals minus C. Arithmetic comes out here. We take the ratio of S to E, and it's about 2.43. That's arithmetically. From a statistical point, it's about 2.5. So, you know, don't believe those digits. Students handed a number 1.7482937. That's what my calculator said, but it's wrong by 15 factors of 10. Okay, anyway, the ratio is about 2.4. The solar effect is larger. Okay? And we're talking about the subtle effect of the changing orbital parameters. And so we have there S equals 2.4 E and so forth. So the solar effect is about twice or 2.5 times as large as all the combined earthly effects thrown in together. That's dihydrogen monoxide, aka water, CO2, albedo, various salts, things like that. And what I did, when I took that peak, I'm looking at the time when the CO2 was at the highest, all right, which is more or less our present situation right now. Now the entire temperature change from the coldest depths of the dark age to the ice ages to the warmest temperatures is roughly 12 degrees. And a fourth of that temperature swing is due to all atmospheric and all other earthly effects combined, and therefore no more than about 3 degrees C can be attributed to changes in water, CO2, methane, albedo, and so forth. In other words, nothing to get excited about. Not all peaks are the same if you look at that data. I mean, I just looked at one particular peak. But the closer those two lines are to the same slope, then the higher is the ratio of the solar to the earthlier and the solar to the atmosphere. Yeah, the solar effect to the earthly effect is larger if those two slopes are the same. One of the things, I mean, the people that make these models like to say, well, if we get a lot of snow, the albedo is going to increase. But I'm going to show you a little effect here. If you have, the whole idea is if you have some snow on the ground, it's going to increase the albedo of the Earth. Right? Well, not necessarily. So I got a pretty picture to show you here. This is taken from not far from my home. By the way, I was at Connecticut, but I retired to my home in Pueblo, Colorado. Gee, I found I had spent more time in Connecticut than I had in God's country. That had to change. So I took early retirement and I went out there. This is taken from, quarter mile or so from my home. The elevation around there is about 5,000 feet. We're in desert country out there. Back in there, the land slopes gently upward, still looking like the plains. It's about 6,000 feet. And up in there, we see some snow that might be perhaps ankle deep. Now, I didn't go up there and measure it, but it might be ankle deep. Maybe to an elephant it's ankle deep. I don't know. Anyway, this part up in here has deep snow. And I haven't been up there to see it, but I know the snow up there is pretty deep because, you know, you can drive up through the mountains and you can see that there's just a terrific amount of snow back there. By the way, I think Monarch Pass got something like 55 feet of snow or something like that this year. It might have been 40 feet of snow. That's quite a bit of snow. The South Pole, by the way, the skiing report is very simple. 0.2 of an inch of new snow, 2 miles of pace. Anyway, why don't we see that deep snow up there in the mountains? And the answer is very simple. The snow lands on the trees, and then a little breeze comes along, shakes off the snow, and the snow goes down to the ground, and it shows the trees. Okay? So that the effect of the snow on the albedo in that particular region is minuscule. Okay? I don't think you'll find that in the ICCC, but you can look. So, but anyway, there is an asymmetry, and it looks a little bit like this. Suppose you have an ice age, and an ice age has come along and scraped the ground clean and so forth, and then the snow recedes. As soon as the snow recedes, you start getting a change in albedo, because now you've got bare ground there. But if you're going the other way around, as the Earth is entering an ice age, you've got the snow has to pile up very deep before it begins to cover up all of that vegetable matter and start having a big effect on the albedo. And you see, that is something that also contributes to the asymmetry that we have seen, where the temperature rises a lot faster than the temperature decrease. And of course, since we found out that all those earthly effects amount to no more than about 3 degrees anyway, that means that we can attribute even less of that to CO2 effect. So the conclusions are the following. The fluctuations in the Earth temperature are caused at least 75% by astronomical phenomena. Now, this is not accounting for variations in the sun's output. This just changes in the Earth's orbit. And the combined effects of greenhouse gases, albedo changes, and other things account for no more than about 3 degrees of the changes that have occurred between the depths of the ice ages and the warmest times. And that being my talk, and I thank you for your attention.